There are three general exceptions that we need to keep in mind when we draw Lewis structures that exempt particular structures from following the octet rule. For one, if we have an overall odd number of electrons, then it will be impossible for every atom to feel like it's got 8 around it. In a second case, we could have electron-deficient central atoms, those that cannot hold 8 electrons around them. And then lastly, we can have molecules whose central atom has an expanded octet that accommodates more than 8 electrons around it. So let's go through these one by one. In our first example, we say that a molecule like nitrogen monoxide, NO, has an odd number of valence electrons. If we try to draw the Lewis structure for NO, our electron budget will show 5 valence electrons from nitrogen, 6 total valence electrons from oxygen. That means that we need a total of 11 electrons shown in the Lewis structure for this molecule. When we draw this Lewis structure, we'll draw a nitrogen atom with 5 valence electrons, an oxygen atom with 6, and we'll connect some dots, say right between these two. At this point, neither the nitrogen nor the oxygen atom feels like it's got a satisfactory octet. We could promote 2 electrons, one from each of these atoms, to a shared pair between them and create a double bond. But we'd see, even with this double bond in place, that the total number of electrons, while matching our electron budget, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, still renders this molecule as a whole without an octet on our nitrogen. Nitrogen only feels 1, 2, 3, 4, 5, 6, 7 electrons around it, while oxygen's octet is satisfied. There's no way that we can reconcile this unpaired electron over here on nitrogen. And the best we can say about this Lewis structure is that this is as good as things get. We can verify later with formal charge, but for right now, we'll just say that this particular structure is as close as we can come to satisfying the octets on every atom. So this is the Lewis structure for nitrogen monoxide. It has 1 unpaired electron in it. The presence of that 1 unpaired electron renders this molecule highly reactive. In fact, unpaired electrons in molecule structures are called radicals. That 1 unpaired electron is called a radical electron. And it serves to frame the reactivity of this molecule. We expect that NO will try to seek out any source of partnership that it can to stabilize that unpaired electron. We expect that when we see Lewis structures whose electron budgets have an odd number of electrons, we'll end up with radicals as a result. In the Lewis structure for boron trichloride, BCl3, we expect just 3 valence electrons from our boron and 7 from each of our chlorines. In total, we'll have 24 valence electrons depicted in the Lewis structure for boron trichloride. Our lowest electronegativity atom is boron. It shall go at the center of this molecule, and we'll place chlorines around it, each with 7 valence electrons. After we've connected dots, we'll end up with a central boron bound to 3 chlorines. We'll see in this Lewis structure a total of 2, 4, 6, 8, 16, 24 electrons, just like our budget calls for. And we'll see that each chlorine feels 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So every chlorine's octet is satisfied. All of our chlorines are happy, but our central boron atom only feels 1, 2, 3, 4, 5, 6 electrons. This is the only way that we can draw this Lewis structure. And again, once we consider formal charges in the next video, we'll understand that this is the best Lewis structure for boron trichloride. But it leaves boron feeling only 1, 2, 3, 4, 5, 6 electrons around it. We say that in this Lewis structure, our central boron atom is electron deficient. It doesn't have a full suite of 8 electrons around it, simply because it didn't have enough electrons to share, to make it to 8. Atoms like boron and beryllium are typically incapable of satisfying a full octet, given that they don't have enough shareable electrons in their valence structures to do so. Finally, if we think about sulfur hexafluoride, SF6, we'll need to draw a Lewis structure that has 6 electrons from our central sulfur atom and 7 from each of our fluorines, for a total of 48 electrons overall in our structure. Sulfur again can go at the center of the structure. It's got 6 valence electrons. Each fluorine atom I'm going to place around sulfur so that an unpaired electron on fluorine matches up with one of the electrons around sulfur. And now we can begin connecting the dots between fluorine and sulfur. What we'll find is that even though each of our fluorines satisfies an octet, 1, 2, 3, 4, 5, 6, 7, 8 electrons around each one, and we show a total of 48 electrons, 8 times 1, 2, 3, 4, 5, 6, that our central sulfur atom has more than 8 electrons felt around it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The only way to get sulfur and 6 fluorines to bond is to make sulfur feel like it's got more than an octet worth of electrons around it. We say that sulfur has an expanded octet. It's accommodated more than its requisite number of electrons around it, and as such, its octet has expanded. The only elements for which we can see expanded octets are those whose valence electron shells have at least the capacity to house d orbitals. D orbitals can be found beginning in the 3rd energy shell, and elements whose valence electrons are in the 3rd energy shell begin in row or period 3 on the periodic table. The only times that we can see elements with expanded octets are when those elements come from the 3rd, 4th, 5th, 6th, or so on rows of the periodic table. These elements all have valences that at least can house d orbitals, and as we'll see in a future discussion, it's these mixing of d orbital phenomena that allow an element to expand its octet in the first place. So to summarize, we'll see exceptions to the octet rule anytime we've got an odd number of electrons in our electron budget, anytime we're dealing with electron deficient central atoms like beryllium and boron, and whenever we've got an element as a central atom from period 3 or below on the periodic table that expands its octet. Each one of these Lewis structures that we've drawn today can be evaluated in the form of formal charge to verify that they are the best Lewis structure. We'll talk about formal charge in the next video.